Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I am Arif and I welcome you all in today's session. To access the notebook for today's session, you can access course page on my personal website arifbhat.me. The other way is to download all the notebook files from the course GitHub account Arif PUCIT, and all the notebooks for this course are housed in this public data science repository. Well, this is the Jupyter Notebook dashboard running locally on my machine at port 8888, and here is the notebook for lecture number 6.6 of the sixth module, Overview of Machine Learning, for the course titled Tools and Techniques for Data Science. The title for today's session is Linear Regression using a Scikit-Learn library. Well, my dear friends, this is a continuation of our previous sessions on regression, which is a statistical technique that describes the relationship between a dependent variable to one or more independent variables. In the due course of our sessions, we have learned about different regression types like linear, polynomial, ridge, lasso, logistic, and so on. But today we will mainly talk about implementing linear regression using the Scikit-Learn library. So let's move on to the agenda of today's session. Today we will go step by step, and I will try to cover all the steps and their nitty-gritties in our Scikit-Learn workflow for supervised machine learning. So I have divided it into roughly 10 phases that we will cover on our sample dataset, starting from data acquisition to finally model deployment. Well, my dear friends, this is a generic workflow of a supervised machine learning task. It starts with data acquisition, then we perform some data pre-processing to make the data ready to be fed to a machine learning algorithm. Once done, we need to choose an estimator or a machine learning model that best suits the dataset and the problem at hand. In order to check the accuracy of our trained model, later we divide the datasets in two parts: our training dataset on which the model is trained and the test dataset on which the model is evaluated. The next step is to create an instance of the model. Then we train it and evaluate the model on the test dataset which the model has not seen during training phase. And if we are not satisfied with the model's performance, we may need to do some hyperparameter tuning. And the final step is to deploy the machine learning model into a live environment from where it can be accessed by the end users to perform the prediction. Okay, so let me go through all these phases one by one using a sample dataset. My dear friends, for the learning purpose, you can use built-in datasets that come bundled with the Seaborn's Scikit-Learn and Natural Language Toolkit library. In the last session, we explored different toy and real-world datasets that we can get using the load underscore and fetch underscore methods of Scikit-Learn datasets module. We also saw how to use the fetch underscore OpenML method to get any dataset from the open machine learning repository. And in addition to that, we also use the make underscore methods to generate artificial datasets of controlled size and complexity. Well, in our previous sessions, we have also seen as to how we can acquire data from a company's database and scrape data from different websites. And in our next sessions of machine learning, I will not be spending much time on this phase and will assume that we have the dataset somehow, so that we can spend more time on the task for which this module is all about, that is machine learning. Let me load this advertising dataset on which we have worked in our video session number 6.3 as well. That is the advertising dataset. This dataset is of an advertising firm. The three input features shows the expenditure spent on TV, radio, and newspaper ads in thousands of rupees. The output column sales shows the number of items or maybe widgets sold in thousand units. Well, being a data scientist, the company asks you that you should see this data set and advise them as to how should they spend their advertising money in the future. So these are some of the questions that you need to answer. First of all, how strong is the relationship between input features and output sales? Which advertisement type, TV, radio, or newspaper, contribute more to sales? What is the effect of each ad type individually on the sales? And given a advertising budget, how can we predict the future sales? My dear students, before we start searching for the answers to these questions, let's see if we need to do any sort of data pre-processing and feature engineering on this data set. Okay. Well, data pre-processing and feature engineering is a very important phase of all the machine learning algorithms. In this phase, we actually remove outliers from the data, if any, and make sure that the data is in a usable format for our machine learning model. The Scikit-Learn pre-processing module provides a bundle of utility functions and transformer classes for data pre-processing. And this phase is so important that I have decided that I will have a separate session on this, maybe the next one. However, in today's session, let me just give an overview of the pre-processing task, which I have divided into four main categories. And let me describe these with the help of this sample housing dataset. First of all, if you see under the schools nearby column and some other columns as well, we have null values represented by NaN or not a number. Before feeding this data to the machine learning model, we need to impute the machine missing values. Moreover, if you see under the number of bedrooms, this column, you can observe the value 44, which seems to be a typo. So we need to correct it somehow. Otherwise, our machine learning model will learn something wrong, which it should not. And to check out for null values in our advertising dataset, one way is we can use the info method of the data frame. We have the data frame in the variable df. So let me check out info. Okay. So we don't have any null values in our advertising dataset. You can see over here. And similarly, to check for outliers, you can either use the describe method of the data frame, or you can also use a box plot if you want to visually see it. Let me use a box plot on our dataset, and let me use the box plot method of Seaborn library, sns dot box plot, and let me pass it the, let's suppose, the newspapers column. Okay, so we do have two outliers under the newspaper column. The min is around 0, first quartile is at 12, second quartile is roughly at 25, third quartile is at 45, I think, and the max is at roughly over here, but if we talk about this outlier, it is roughly 114. Now, how to handle the missing values and outliers? will be dealt in a separate session, of course, as I've already said. Okay, so we have talked about imputation of missing values and handling outliers. The next pre-processing strategy is transforming information. Well, Sklearn provides a lot of transformer classes for this task. The two very common transformers are for encoding of categorical features and feature scaling. Let me describe these two one by one. Note this city column has textual data, or you can say that there are four unique cities under this column: Lahore, Karachi, Islamabad, and Sheikhupura. Machine learning algorithms require input data in numeric format. So we need to convert these categorical variables to numeric values using some encoding techniques, like maybe label encoding or one hot encoding. Fortunately, we do not have any categorical variables in our advertising dataset. So we can skip this phase. The next transformation is feature scaling, as shown over here, which is done on real valued input and output variables. Well, my dear students, in a dataset, different features may have different units or scales. For example, some columns may have their values in feet, some columns may have values in kilometers, in hours, in years, and so on. And some machine learning algorithms are really sensitive to these feature scales. For example, for gradient descent based algorithms like linear and logistic regression and neural network, we need to do feature scaling. Similarly, for distance-based algorithms like k nearest neighbor, k mean, and support vector machine as well, we need to do feature scaling. However, tree-based algorithms they just split a node based on a feature. Therefore, they are not sensitive to the scale or units of the features. So we do not need to do scaling for tree-based algorithms. And this feature scaling is further categorized into two types: normalization and standardization. Well, this normalization rescale the values between 0 and 1, while this standardization rescale the values so that they are centered around the mean with a standard deviation of 1. Well, my dear friends, next $100 question is when we need to do standardization and when we need to do scaling. So we use standardization when the data follows the Gaussian distribution, and we use normalization when the data does not follow Gaussian distribution. And fortunately, all the input features of our advertising dataset have the same units, and that is in thousand of rupees. So we do not need to do a scaling in our advertising dataset. My dear students, the third pre-processing task is extracting information. Uh, Consider this construction date column or feature in our housing dataset. Uh, Over here, we may need to extract only the year from every cell of this column, which we want to feed to our machine learning algorithm for training, so that our model should predict the price of the house based on only the year and not based on the month and the day. Finally, the fourth pre-processing task that you might need to do on your dataset is combining information, which is done by merging multiple columns to lesser number of columns. For example, in this housing dataset, the three input features like the size, number of bedrooms, and number of bathrooms, they can be reduced to single feature or column, that is size, and this is also known as dimensionality reduction. My dear students, don't worry. I will of course create a separate video session on how to do all these data processing and feature engineering tasks. For the time being, let's move on to the next phase, that is choosing the machine learning model. Okay. Well, there are many models or estimators that researchers and data scientists have created over the years. And some are very well suited for numerical data, some are good for textual data, while some are good for image data. So the right model for your data depends on the type of the data you have and what you want to do with it. Well, this sort of flowchart is designed to give users a rough guide to choose an estimator to try on your dataset. First, let's talk about the regression task. If you have more than 100 case samples in your dataset, you should prefer stochastic gradient descent regressor as it has less time complexity. If you have less than 100K samples and a few important features, use lasso or elastic net regressor. And if you have less than 100K samples but more features, use ridge or sport vector regressor. If these estimators show low performance, high bias or high variance problems, then you should try some ensemble technique. Let's move on to the classification. Well, once again, if you have more than 100 case samples, you should prefer stochastic gradient descent classifier as it has less time complexity. If you have less than 100K samples, you should use a support vector classifier or maybe a K nearest neighbors classifier. Once again, for textual data, naive Bayes classifier give good results. And once again, if these models show low performance, high bias or high variance problems, then you should try some ensemble techniques. And finally, if the output is mm, categorical but you do not have labeled data, you should use some clustering algorithm like k-means or mini-patch k-means or Gaussian mixture model. And of course, we will talk about dimensionality reduction in some later part of the course. Okay, so let's see our data set once again. That is there in DF. Our three independent or feature or predictor variables as well as the dependent or output variable sales are having continuous values. So we are good to apply some regression model. However, we have to dig down a bit in order to determine the type of the regression model that we should use. And before we apply linear regression, we need to check out that all the feature variables should be somehow correlated with the output variable, but not with each other. And these first two assumptions can easily be checked using scatter plots. And this third assumption can be verified after we are done with the training of our model, and that is to check for homoscedasticity. That can be done by a residual plot and ensuring that the residuals or errors of the regression line are approximately normally distributed. We will of course check this one as well. But for the time being, let me check out the first two assumptions by drawing scatter plots among all these variables. We have done this in our previous session as well, but this time let me use a simpler way, that is the pair plot method of Seaborn. SNS dot pair plot, and let me pass it the entire data frame. Great. So there are 16 subplots, 4 on each row. You see over here we have TV, radio, newspaper and sales, and over here we have again TV, radio, newspaper and sales. These two scatter plots at the extreme right shows that there do exist some linear relationship among TV on the vertical axis and sales on the horizontal axis, among radio and sales, these two scatter plots. However, if you see this scatter plot that is between newspaper and sales, uh, this shows that there exists no relationship between the two variables, that is newspaper and sales. So we may think of dropping the feature newspaper, as it appears that it do not have any impact on the output sales. But for the time being, we are keeping it. Similarly, you can observe that the scatter plots among the input features themselves over here, they are almost random. You can see that we have random. This radio and TV, it's almost random. Newspaper and TV is almost random. So we can conclude that all the feature variables are not correlated, or all the feature variables are independent. So I think we are good to go for applying linear regression model on this advertising dataset. I hope this makes sense. So let's move on to the fourth phase. My dear students, after you are done with choosing an appropriate model or estimator, the next task is to train it on the available dataset. But if we train our model on the entire available dataset, how can we later evaluate the trained model? Because true evaluation can only be done if you test your trained model on a data which it has not seen before. And one possible solution to this is train, test, split. And the main idea behind train, test, split is to split the available dataset in two parts. One part is called the training dataset, on which you will train your model, and the other part is called the test dataset, using which you will later evaluate your trained model. There are different strategies using which you can do a train, test, split. The most common is that you shuffle the data and choose a random fraction for test. Now the question is what fraction you should keep for test. This depends on the number of records you have in your data, as well as on the complexity of the model. And mostly we use a split of 80-20. And this entire process is described in this image, having two data sets. The left one is for classification, and the right one is for regression tasks. And I think we have described these images in our first session as well. Anyway, let me repeat. In this image of a hypothetical housing dataset, we have a total of 9 observations, and we are keeping 7 for training, shown in this blue box, and 2 for test, shown in this purple box. In order to train the model, we give it the 7 4-dimensional feature vectors and the corresponding output labels, and the model learns the relationship between the input feature and the output label. And once the model is trained, we give the model the test dataset, that is this one, only the input features, and it carries out the prediction. And later we compare the predicted values with the true or the actual output values to see how good or bad our model is performing. So now I think we have a fair idea about our train, test, split of dataset, training of model, evaluation of model. Let's move ahead and do all these things practically using Python. Okay. Uh, let's once again see the entire available dataset, which is there in the data frame df. Great. So we have 3 input features, 1 output label, and a total of 200 observations. Let me first separate the input features and output label. And we normally store the input features in a capital variable x, just convention. We can do it using df.drop method. We just drop this sales column along axis is equal to 1. This is a very quick way of doing so. So we have our x with us. Let me see it. This is capital X. Okay. So now we have a data frame that contains only the input features. Similarly, we keep the output variable in a variable named lowercase y. by convention, and this can be done simply like this. Great. Do note that both X and Y have 200 rows. This also has 200 rows. Note the indexing of this data frame, and this also has 200 values. Note the indexing of this series object. Uh, for example, for the input features at index 2, the three-dimensional feature vector has values 17.2, 45.9, and 69.3. And the corresponding output for this feature vector is also at index 2 over here, uh, and has a value of 9.3. I hope this is making sense. Okay, now we need to divide this x as well as y into two parts, and this can be done using the train test split method of the model selection module of Scikit-Learn. Let me do that from Scikit-Learn dot model selection. I need to import the train test split method. And in some future section, of course, we will talk about the cross validation techniques as well, which are used to simulate multiple train test splits on the available dataset. Fine. So after importing it, let's use it. Train test split. Let me press Shift Tab to go to the help page. And this is the help page. If I scroll down a bit, you can see that this is how it is used with the parameters. So let me just copy paste. So this is a good practice because this method actually returns a tuple which is unpacked over here. So the four values which this method returns are the x train, x test, y train, and y test in the same specific sequence. It is passed x and y. Well, this test size, as I said that we are going to keep it 80-20. So this shows the fraction of the test dataset. And this random state, let me keep it to my favorite number 54. This is very similar to setting a random seed in NumPy. You can use any value of your choice over here, but make sure you use the same value if you intend to use multiple algorithms and later compare their performance. Actually, my students, the trained test split method will shuffle the dataset before doing a split. If you change the random state value, the shuffle will vary and you will have different observations in the training and the test dataset. Let me execute the code of this cell and let's look at the sizes. Let me look at the size of df. Let me look at the size of x train. Let me look at the size of y train and x test and y test. Let me execute. Great. You can note that we have a total data set of 200 values. Now the X train and the Y train both have 160 observations. X test and Y test have 40 observations, which makes sense because the test size argument is set to 0.2. That is 20% of the portion is kept for the test data set. Great. Let's see that. X train. Let me execute it. So this is the X train. Let me see the Y train as well. Good. But if you note the indices in the X train exactly correspond to the indices in the Y train. You see the indices, they are random. So this way we'll be able to match the X train rows with the corresponding Y train rows. And the same hold, of course, true uh, for the X test and Y test as well. Let me show that to you as well. X test. Let me show the head only now. And Y test. Once again, let's see the head only. You see, this is the first 5 records of the X test, and these are the first 5 values of the Y test. Note the indices. Great. My dear friends, once again, remember the main purpose of our doing the train test split is to fairly evaluate our model. Let's move ahead. Now it's time to create an instance of the linear regression model. Remember in Scikit-Learn, an estimator is actually a Python object that implements the fit and predict method. To the fit method, we pass xtrain and ytrain in order to train the model. And to the predict method, we pass just the x test to get the prediction. And this is the classic way of importing the estimator of your choice from Scikit-Learn. That is, you import specific estimator, the specific estimator from the corresponding model family module of Scikit-Learn. Well, a linear model, neighbors, SVM, knife bias, tree, and ensemble are some of the modules with their estimators shown in magenta color over here. Inshallah, I intend covering all these under the supervised machine learning portion of this module, inshallah. And today we will work with the linear regression, this one. And you can try out the SGD regressor as I have already discussed its entire math in our previous session at your own. However, one should use gradient descent when you have a big data set having number of observations around 10k. While in this advertising data set we just have 200 rows. So better to use linear regression. Okay, so let's import the estimator from Scikit-Learn dot the family is there. If you press tab, you can see a lot of families. You can see all the families over here. So I'm interested in the linear model family, and inside linear model family there are a lot of regressors you can see. And right now I'm interested just in the linear regression. And let's see the help page of this. Do make it your habit to check out the help page of the estimator you are working on. So this is the help page. We have examples, we have parameters and so on. But in today's session, we are not going to talk about the hyperparameters much. We will go with the defaults for the time being. So let's create simply an instance of this model now. Let me say linear regression, and let me save it in a variable named lr underscore model, that is linear regression model. So this has created a linear regression model with default parameters. Later, after evaluating the trained model, we may come back over here and do some hyperparameter tuning by adjusting the different parameters of this method and thinking that they might improve the performance or the accuracy of this model. For the time being, let's move ahead and check its baseline performance. Okay, so training. Now that we have an instance of the linear regression model, next step is to train this model on the training dataset. And to do this in Scikit-Learn, we simply call the fit method on the model instance by passing it the xtrain and the ytrain, as we do not want to train it on the entire dataset of x and y in order to fairly evaluate the model later. So let me just say lr underscore model dot fit. So this is the fit method, and I pass it xtrain and ytrain. Great. Remember, this is an in-place method. So now we have a trained model with us. So this model has been trained. The data was quite small, so it doesn't take much time. Let us check out the regression coefficients and y-intercept values by grabbing the coefficient attribute of LR model. Great. So these are the three coefficients. Let me check out for the y-intercept as well. Dot intercept. This is y-intercept. My dear students, you can compare these regression coefficients with those that we computed in our video session number 6.3 without using Scikit-Learn, rather using the closed form solution using NumPy. I think we have used the ordinary least square method with matrix algebra at that time. Let me now describe as to how we can interpret these coefficient values. Well, since there are three input features in our dataset, so there are three regression coefficients. Beta 1 is 0.46 roughly, which correspond to the weight of the first feature, that is TV. This says if you hold the other two features, radio and newspaper, fixed and only adjust TV, then increase in 1 unit of the TV ad will result in an increase of 0.46 units of sales. I hope this makes sense. Similarly, this beta 2 is 0.185, which correspond to the weight of the second feature, that is radio expenditures. And this beta 3 is minus 0.003, very small value in negative, which correspond to the weight of the third feature, newspaper. Let me describe these from the data set. Let me say that we have the data set df.head. Now this will make more sense. Well, consider this first observation. Excuse me. Well, if you increase TV by 1 unit, that is from 230.1 to 231.1, by keeping radio and newspaper fixed, you would expect to increase your sales by 0.046. That is from 22.1 to around 23. Similarly, if you increase radio by 1 unit, that is from 37.8 to 38.8, by keeping TV and newspaper fixed, you would expect to increase your sales unit by 0.185. That is from 22.1 to 26.1. Now this negative coefficient for newspaper is interesting. It says holding TV and the radio expenditures fixed, for every unit increase you spend on newspaper advertising, you should expect a drop in sales of 0.003. So a negative coefficient of newspapers actually means it is going to lower your total sales. My dear students, we also observed this from the scatter plot of newspapers and sales with a very small correlation coefficient showing no relationship between newspaper and sales. So in simple words, this very small negative regression coefficient for newspapers, it suggests that the company need to not to spend anything on newspapers advertisement, as it is not worth the effort. But for the time being, we are keeping this because later we will see that when we will talk about the synergy concept, it will help us a bit. Finally, this intercept value of 3.05 is beta 0, and this shows that if we spend nothing on advertisement, that is keep all the input features as 0, the sales will be of 3.05 units. I hope now you have a fair idea as how to interpret the regression coefficients of a linear regression model. So let's move ahead. Okay, my dear students, once we are done training our model, the next task is to check out how accurately our model is making the predictions. And this is where the dataset that we set aside earlier comes into play. That is the X test and the Y test. And remember, Evaluation allows us to check the accuracy of our trained model by testing it on data that has never been used for training or which the model has never seen. And this is actually the representation of how the model might perform in the real world once deployed. Let me show you the X test data frame and the corresponding Y test series. X underscore test. Let me show you the head only. And let me show you the Y test, just the head of it, because I don't want to show you the 20 values. I will not be able to compare that in that way. So there are these are the first 5 records. Note the corresponding shuffled indices. The first row is of serial 179, saying if you spend on TV, radio and newspaper ads 165.6, 10 and 17.6 thousand rupees, then the sales will be of 12.6 units of the product, maybe 1000 units of the product. And the output is of course there in the Y test. So these are the real or the actual Y labels. Let us now give our trained model the X test data only to predict the output sales, which we will later compare with the ground truth or the real values or the actual sale values to check the accuracy of the model. And to do this in Scikit-Learn, we simply call the predict method on our trained model by passing it the X test. Let me do that. lr model dot predict is the method, and I'm passing it just the X test. And of course, this will return the predicted Y values. So let me name it predicted, predicted, and let me display it for you. Let me just show the, rather this will be a list, I think. Yes. Okay. So we have got 40 predicted Y values for the 40 input rows. Note that this is 12.6 and this is 12.4. So this is the actual Y label and this is the predicted Y label. So this is 8.0, the actual Y label, and this is 10.7, the predicted Y label. Let's check the residual errors now. Let me say that test underscore residuals is equal to Y underscore test. That is the actual true Y labels minus Y underscore predicted, which we have computed over here. And let me display those as well. So these are the residuals. Note the real output for input at serial 179 is 12.6, and our model has predicted output as 12.47, and of course the difference is 0.12. Great. Now, my dear friends, there are different evaluation metrics that compare the predicted Y values with the actual Y values and tell us how well our model is performing. The most commonly used evaluation metrics used for evaluating regression algorithms are shown over here. Yes. I think we have discussed them in our previous session as well, but let me quickly describe them again. As one of my teachers once said, that a teacher is someone who always repeats. Okay, mean absolute error. This is the sum of the differences between the actual Y values and the predicted Y values. We divide the resulting value by n to take the mean, since the differences can be positive as well as negative. So we take the absolute value to make sure that we don't average out to 0. Well, the limitation of mean absolute error is that it does not punish the outliers. So to fix this, we take the square of the differences, which will punish the larger errors, and This is what is shown over here in mean squared errors. And this is obtained by the sum of the squared differences divided by n. So squaring the residual errors is really going to increase the overall effect on the average of those outliers. However, this mean square error has its own limitation. And the limitation is that the error it returns is in different units than the actual unit of the output label. For example, if the unit of the output label is in rupees, then the unit of the mean squared error will be in squared rupees. So saying that our predictions are off by this much squared rupees is actually hard to interpret. So to fix this limitation of mean squared error, we take its square root and call it root mean squared error. My dear students, we can calculate the three error metrics using these formulas with the Scikit-Learn metrics module also come bundled with lot of evaluation methods for our trained machine learning models. Let me use them. And for that, let me say from Scikit-Learn dot metrics. Okay, so this is the module. From this module, I can import a lot of evaluation metrics. This is a huge list, and let me for the time being just use mean absolute error, and let me use mean squared error. Okay, and now I can say that MAE, that is mean absolute error, is equal to mean absolute error, and I need to pass it the, of course, y test and the y predicted, which I have computed above. Note this is the y predicted, this one. Great. And similarly, I can calculate the mean squared error as well. Mean squared errors, and I need to of course pass it again the y test as well as the y predicted. Well, I couldn't find the Scikit-Learn method for calculating the root mean squared error, so we can calculate it manually. RMSE is equal to, I can use the SQRT method of NumPy and pass it MSE. Let me print out MAE. Let me print out MSE as well. I hope I'm not making any typo. Let me print out RMSE as well. And let me execute it. Great. Okay, so the most popular metric is RMSE, which is going to punish the large errors by scaling them, and also fixes the issue of scared units of output label by taking the square root of the result, and that is 1.46. Now, my dear students, the next question that comes to students' mind is, how can we interpret this error value? So, my dear students, this 1.46 value of root mean squared error says that by average the model predictions are this much off from the real value. And the next natural question that may come to your mind is this error value good or bad? Well, to answer this question, let me check the average value of our output sales. Let me check out the average value of sales that is there in this column. Let me apply the mean method on this. So that is 14.0. Okay, so the average sales is 14 units or 14,000 units, whatever the units of sales happens to be. Therefore, RMSE value of 1.4 can be interpreted as roughly a 10% error. The next question the student might ask is a model having 10% error a good model? Well, the answer to this question depends on the context. If the model is predicting the price of a house, then I think a 10% error rate is okay. But if the model is predicting some medical results, then a model giving a 10% error is a complete failure. Okay. My dear friends, the fourth evaluation metric that I want to discuss is R2 score, which does not tell the error, rather tell the performance of your model. R squared is also called the coefficient of determination since it is the square of correlation coefficient, and that is why it is called R square. And the formula to compute it is shown over here. That is 1 minus sum of square due to errors divided by total sum of squares. I think I have discussed this as well in our previous session, maybe 6.2. And the sum of square due to errors and sum of square due to regression, as well as the total sum of squares, is described in this left graph. Let us calculate it using the R2 score method metric of the Scikit-Learn library. For that, I just have to do from Scikit-Learn.metrics import R2 score, and let's say that R2 is equal to R2 underscore score, and we need to pass it, of course, the y underscore test and y underscore predicted. So we have the R2 now. Now I just need to print it. R2 score is R2. Let's run it. Great. So let me interpret this value of 0.917. It actually says 91.7% of the variance in the sales column of our advertising dataset is accounted for by the three input features. The value of R2 score can range from 0 to 1, which is shown in these graphs over here as well. The value of 0, which is shown in this rightmost graph, says that none of the variance in the output variable is accounted for by the input feature variables. Well, my dear friends, the limitation of R2 score is adjusted in adjusted R2 score. Yes, over here. The limitation of R2 score is that if you add more features to your model, the R2 score will increase or stay the same, but will never decrease. Adjusted R2 score is a modified form of R2 score whose value increases if new predictors tend to improve the model's performance and decreases if new predictors do not improve performance as expected. The formula is shown over here, which we discussed in detail in our video session number 6.3. Once again, I couldn't find a method to calculate the adjusted R2 score in Scikit-Learn's matrix module. So let's calculate it using this formula. Let me say that in this formula, we have n is the length of the observation x test, and m is the number of features, that is 3. R2 underscore adjusted is equal to, the formula says 1 minus R2 multiplied by n minus 1, yes, and then divided by I think n minus m minus 1. So this is what the formula is, and let me print it. Print R2 adjusted is R2 adjusted. I think, yes, great. So adjusted R2 score is almost the same as R2 score. Great job done. Okay. My dear friends, before moving ahead to hyperparameter tuning phase, let me take this opportunity to tell you as how a residual plot can help us determine whether or not a linear regression model is appropriate for a given data set. Well, consider these four scatter plots of 4 different data sets, each having 11 data points xy. And these 4 datasets were constructed by a famous statistician, Francis Anscombe, in 1973. and they all have nearly identical descriptive statistics. The mean of all the four x columns is 9, while the mean of all y columns is 7.5. Similarly, the variance of all the four x columns is 11, while the variance of all four y columns is 4.125. The correlation between x and y in all the four datasets is 0.816. You can compute this at your own. However, if you apply a linear regression model to fit a best fit line, the slope of the regression line for all the four datasets is zero point 0.5, and the y-intercept is 3. And this can be seen in these four scatter plots. And finally, the R2 score, or coefficient of determination of linear regression, for all these four datasets is 0.67. So this is a great dataset, Anscombe Quartet. Since all the datasets are having one dependent and one independent variable, therefore by plotting their scatter plots, one can easily make out that the datasets that correspond to the top right and bottom right graphs are not suitable for linear regression at all. My dear students, this seems simple and great, but this is nearly impossible to visually differentiate if we have three or more input features. And the solution is yes. We draw scatter plots with residual values along the vertical axis and the true y values along the horizontal axis. And of course, this can be drawn irrespective of the number of features we have. Well, the top row of this image shows four residual plots corresponding to four different datasets. If you observe this top left plot, you can observe that it has high density of points close to the origin and low density of points away from the origin. Moreover, it is symmetric about the origin. Since all the residuals are evenly distributed across the graph, so there exists constant variance. In these two middle graphs, the residual errors are large on one side than the other. So there exists non-constant variance, and we call it heteroscedasticity. And I think we have discussed this as well before. And there exist, of course, different ways to fix heteroscedasticity from your dataset, like transforming the dependent variable, redefining the dependent variable, or maybe use weighted regression. Finally, this top right graph, if you see it, the points are in the shape of a curve. So the linearity assumption is violated. So better use some non-linear model, or you may try identifying the transgressing variable using some curvature test. And remember, by transgressing variable, I mean the independent variable having non-linear relationship with the dependent variable. Well, my dear students, I think that much detail is enough for today's session. Inshallah, in future session, we will talk about polynomial, uh, logarithmic, exponential, and sinusoidal regression as well. And let me move ahead. And let me draw the residual plot for our advertising dataset. So we do have test residuals. Yes, we have. Let me compute it again. Y underscore test minus y underscore predicted. So these are the test residuals. Let me draw the scatter plot. Along the x-axis, I keep the y underscore test, and along the y-axis, I am keeping the test underscore residuals. Great. Let me label the x-axis. X label as, let me say it, sales, and let me label the y-axis as well, y label, and let me say it residual errors, and finally let me draw a horizontal line as well, plt dot axh line. Yes, so let me draw it at y is equal to 0, and let me give it a color, okay, is equal to red, and let me give the line style as this, and great. So this graph more or less looks random. There is no clear line or curve. So for this data set, I think linear regression is an okay model. Good job done. Let's move ahead. Well, my dear friends, after we have evaluated our trained machine learning model, we can try improving its performance via hyperparameter tuning. And one must know the difference between models per parameter and hyperparameters. Well, a model's parameter are variables which a model learns at its own during training. For example, slope and y-intercept are the parameter of simple linear regression model. On the contrary, our model's hyperparameters are configuration variables that are explicitly defined by the machine learning engineer to control the learning process before the model starts training. For example, the learning rate and number of iterations are the hyperparameters of gradient descent algorithm. Today, I'm going to skip the step of hyperparameter tuning and instead assume that we are fully satisfied by the test metrics of our linear regression model. We will talk about hyperparameters in our future session, inshallah. So let's move ahead to the last phase, that is the deployment phase. Excuse me. My dear friends, once we have trained and evaluated our model, the final step is to place our machine learning model into a live environment from where it can be accessed by end users or maybe by other applications using an API. We will inshallah have a separate session again on deployment of the machine learning model since today's session has gone a bit long. However, today let us serialize and save a trained model on disk and load it to do the prediction then. And let me just create a new model instance for that purpose. Let me say uh, final underscore model is equal to linear regression. So this is a new instance of the model. It should be the exact same model with same values of hyperparameters on which our model is tuned. And after creating the instance, we fit or train it on all the data, because at this point we have decided that the model hyperparameters are good enough. So when we deploy it for the end users, we want to take full advantage of the entire dataset, which is of course the full X and full Y. So I say final model and I pass it full X and full Y instead of the just X train and Y train. So we have some error over here. So what's the issue? Fit model dot. Sorry for this. So the model is now saved in this variable final underscore model. Now we just need to save it, and for this we can either use the pickle or the job module, job lib module. Since the job lib module is more efficient, so let's use it. From job lib, we just need to import its method dump, and let me use this dump method to dump this model on disk. Final model, and let me say the name of the file is adv underscore model dot job lib. So the model is now saved on disk in the present working directory. My dear friend, you can always now send this file to the company rep who can load and use it. Let me do that as well. From job lib, this time the company rep needs to use the load method, and let me load it in loaded model, and the name is adv underscore job lib. So we have some typo. Great. Now we need to carry out a prediction. Suppose we want to predict the sales if the company spent 200, 150 and 0,000 rupees on advertisement respectively on TV, radio and newspaper. Let me do that now. I say the loaded model dot predict, and let me pass 200 comma 150 comma 0, and let me execute it. Great. So the model has predicted to get a sales of 40.3 thousand items for this particular campaign of advertisement. Hopefully this is correct with a root mean square of 1.46. I think that's enough for today. Uh, I think we have covered all the agenda items. Hope this was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning and Allah Hafiz.